Now we're going to look at the exponential model for growth and decay. It's exponential because the growth rate depends on how much there is. So if you imagine if you put $100 in the bank and you put it at compound interest, then as the principal, as you gain interest, the interest is added, and then we increase the amount by more and more as it grows. So this is an example of exponential growth or compound growth. So the rate at which it grows depends on how much is present. So the more there is, like population's another good example, the more people, the faster the population grows. If we look at, say, carbon dating and radioactive decay, the amount of radioactivity or the amount of carbon in a substance decays, it gets less and less, and depending on how much there is. So let's just look at the model. Let's go through it. N is the initial amount. Now, if we're talking about a population, that's the initial population at the start. If we're looking at decay, where something is getting less and less, well, that's once again, it could be a weight of some sort of substance at the time we start counting. So E is just the exponential number, which we all know. K is the growth factor. Now there are two possibilities. If it's positive, we have growth. If it's negative, we have what's called decay. In other words, it gets smaller and smaller. The amount gets smaller and smaller over time. T is time. And T0 or T equals 0 is when you start doing your observation, is the starting point. And N is the amount present at any given time, T. We can use different letters other than N and N0. So just going through it again. So this is the exponential. If K is positive, we're going to have growth. In other words, the thing is growing over time. If K is negative, we're going to have decay. So the amount present will be getting less and less as we go. N0 is the initial amount. K is the growth factor. If it's positive, we have growth, negative decay. T is the time. T0 is the starting point, and that's when you have N0 present. And so N0 equals N, and N is the amount present at any time T. So let's have a look at an example. We've got a population of 436,000 people in 2005, and it grows to 556,000 in 2015. Find K. So we're going to work on the exponential model. Now, because it's population, we might go P equals P0 e to the KT. And we know when T equals 0, that will be our initial starting point. So that'll be the year 2005 is when T is equal to 0. So we're going to actually start our clock in 2005, and that'll be when T is 0. And then T, if we go 2005 to 2015, that's 10 years has expired. So T equals 10, and that will equate to the year 2015. Okay, so when T equals 0, so it will, when T equals 0, we've got P equals P0 e to the k times t. Now t is equal to 0. Now 0 times k is 0. E to the 0 is 1. So p equals p0. But what is it equal to? 436,000. So from this we can say, because all of this is equal to 1, and e raised to the power of 0 is 1, we've got p0 is equal to 436,000. So now we can go back and quote our rule again. We've got p equals, we're trying to find k. So we've got p equals p0, now we know is 436,000. E to the k t. So that's our modelled. We have only used one of the bits of information. We haven't used this yet. So we know that when t is equal to 10, in other words, in 2015, the population is 556,000. So 556,000 equals 436,000 e to the k. Now that is in the year 2015, and we said in 2015 t is equal to 10. And we don't need that line there, a little stray line that came in. So what we need to do is, well, instead of that we can say that's 436,000 e to the 10k. K times 10 is 10k. We now have an equation we need to solve. When we've got exponential equations with base e, it is a good method. We could take base of 10 if we wanted to, but it's going to be much easier to use base e. So we'll go ln of 5, we'll take logs of both sides. Before we do that though, we won't take logs, we've got to get e to the power first. So we've got to get this by itself. So we've got to divide both sides by 436,000. And if we do that to that side, we're going to divide by 436,000 on this side as well. That will allow us then to get, we can leave this as it is, we can cross out those zeros actually, divide both top and bottom by 1,000. So we've got e to the 10k equals 556 over 436. Now we take our logs of both sides. So we take ln of 556 over 436 equals ln of e to the 10k. Now the log of e to the 10k. A log is a power. You must raise log, don't forget, is base e. What have you got to raise e to get e to the 10k? Well, all of that now just becomes 10k. That's log is a power. You've got to raise e. Natural log is log to base e. What is a power you've got to raise e to get e to the 10k? Well, just raise it to the power of 10k. So your 10k is equal to that. So k is equal to, divide both sides by 10, 1 on 10, ln 556 over 436, and you get 0.0243 when you work that out. So that's going to be our value of k. We were expecting a positive value of k because we have a growth factor going. The population is growing, it is getting bigger. So we've got k is equal to that. Now the second part of the question, that was the first part of the question. The second is the projected population in 2030. Now in 2030, go back up here, in 2030, how many years after our initial, now don't forget we said t is 0 in 2005, so t will be equal to 25. So we're going to use t equals 25. So you've got p equals, now p0 we've already said is 436,000, e to the k 0.02, and it's a good idea to keep 4 decimal places here because when you raise that power, if you go to anything less, if you go to 2 decimal places, your answer is going to be way out. So keep 4 decimal places, t. Now when t is equal to, what do we say, 25, t equals 25, we got p equals 436,000, e to the 0.0243 times 25. Now that's a matter of just putting that in your calculator. 436 times e, and it'll go to the power, put that in brackets, and work it out, and we'll get 800,677. So this is an example of exponential growth. Just leave that there for a minute. There's enough information in the question to be able to work out the growth factor. We were expecting a positive growth factor because the population is actually growing from 2005 to 2015, and then we've got to do a projected for 2030. We use the exponential growth model, and we can use any letters we like. This is the initial amount, this is the growth factor, this is the time after the initial observation was made, and this is what the quantity will be after that time. So we use that. We use our knowledge of solving indices equations because we've got, in this case, to solve for k, and then down below it's just a matter of substituting in to find the population after so many years.